As you can see from the figure, object-oriented programming like the Simula 67 programming language and the logical and procedural programming models as used in languages like C and Pascal were developed at about the same time. Previously, COBOL and the procedural programming model dominated enterprise application development. SAP used a macroassembler before ABAP was created. Even today, many developers have more experience with procedural programming than with object-oriented programming. Therefore, this introduction references the procedural model when it explains object-oriented programming. ABAP was created to improve reporting. It was independently developed as an in-house programming language. It was influenced by other programming languages like COBOL and Pascal. ABAP was then extended to form ABAP Objects. Therefore, ABAP Objects unites object-oriented and procedural elements in one programming language. For the object-oriented programming part, ABAP Objects adopted object-oriented concepts for enterprise application development in other languages, for example, Java, C++, and Smalltalk.
Global variables for a program contain data, while subroutines contain functions. Every subroutine can access all global variables.
A typical procedural ABAP program consists of type definitions and data declarations. The data declarations describe the data structure the program uses when being executed. It is possible to encapsulate logic in modularization units, for example, subroutines or function modules. However, at the main program level, there is no special protection for the global data objects. It is possible to read and change global variables from anywhere in the program.
When a function module is called in the main program, its function group is loaded into the internal session. The function group remains active until the main program finishes executing. The system stores the main program and the called function groups in separate memory areas. Even if the data objects of the function groups have the same data object names as they do in the calling program, they do not share the same memory space. Nothing is shared even if the data objects of the function groups have the same name. It is not possible to access the global data of a function group directly from the main program. You can only call the function modules of the function groups from the main program. In turn, the function modules can access other components, particularly the global data of their own function group. Encapsulation also uses the idea that the implementation of a service can be hidden from other components of the system. The reason for this is that the other components cannot and do not need to make assumptions about the internal status of the modularization unit. In this way, the design of these other components is not dependent on the other modularization units being implemented in a specific way. A function group brings together data and functions which manage the data. Encapsulated access to data and services is one of the many concepts of the object-oriented programming model. Therefore, this programming model and the procedural part of ABAP objects support this encapsulation. When implementing the Business Application Programming Interface, or BAPI, BAPIs are implemented as function modules and business objects are implemented as function groups.
The fictional function group S_vehicle provides a user or client with the services inc_speed, dec_speed, and get_speed. These services are the interface of the function group. They all have access to the global data object speed, which belongs to the function group.
The main program cannot access the data object speed of the function group directly.
In order for the main program to work with several vehicles, there must be additional programming and administrative effort. A function group can only refer to one vehicle at a time. The possibility to create several runtime instances using the same program context is one of the key characteristics of object-oriented programming. In this example, you will develop a program to create 4 vehicles, all of which have different characteristics. However, all the vehicles share the same data structure and the same set of functions. They all have the ability to protect their data from outside access.
The features of encapsulation using function groups and subroutines are as follows. You use modularization units to encapsulate functions and data. You can work with the global data of the main program. The features of encapsulation using objects are as follows. You can use objects to encapsulate functions and data. You can create multiple instances or objects. You can perform multiple instantiation. Objects are stored in the same internal session as the program in use. All data areas are separate from each other, which keeps them protected. Unlike in procedural programming, using multiple instantiation in object-oriented programming allows you to create a direct abstraction of a real object. Encapsulation was systematically extended in this programming model.
You can use ABAP object statements in procedural ABAP programs.
To develop ABAP objects, SAP cleaned up the ABAP language in the object-oriented contexts. This means that obsolete statements lead to syntax errors. For a list of obsolete language elements, refer to the ABAP keyword documentation. ABAP prohibits the use of obsolete statements in the object-oriented context. Objects behave like client or server systems. When one object sends a message to another object to ask it to behave in a certain way, the first object is defined as a client and the second object is defined as a server. In object-oriented programming, the services are distributed among the objects in such a way that there are no redundancies and each object offers exactly those services it is responsible for. If an object needs any other services, it requests them from other objects. This concept is known as the principle of delegation.
Alternatively, a different object could even replace the data retrieval object as long as the new object uses the same protocol. These exchanges can also take place at runtime. Some additional concepts in the object-oriented programming model are as follows. Inheritance. Inheritance defines the implementation relationships between classes so that one class, called a subclass, adopts, adapts, or extends the structure and behavior of another class, called a superclass. Polymorphism. Polymorphism is when instances of classes respond differently to the same messages. Event control. Instead of sending messages directly to specific objects, objects can also trigger events. Then, other objects react when the event is triggered. A standardized language is used in the various phases of software development such as analysis, specification, design, and implementation. Because of this standardization, communication is easier when you change between phases. In object-oriented programming, analysis and design decisions have a greater effect on the implementation than they have on procedural programming. Therefore, you should use modeling language or tools to standardize the analysis and design phase.
Object-oriented programming views the real world as a collection of objects like airplanes, cars, and people. Some of these objects are similar. In other words, objects can be described in the same way if they use the same characteristics and exhibit the same behavior. You can group all the characteristics and behaviors of these similar objects into one central class. This class is used to describe every object derived from it. Therefore, a class is a description of a quantity of objects that exhibit the same characteristics and the same behavior. For example, the vehicle, make X of series N, is an object of class car. This object is a concrete instance of its class. Therefore, an object has an identity, a status, or number of characteristic instances, and a behavior. The concepts of identity and status are different from one another. Note, the literal meaning of instance is slightly more specific. It means that the instance of a class is uniquely identifiable. In this chapter, you will make a distinction between instance and object.
In a software context, abstractions are simplifications of complex relationships in the real world. You can abstract a real, existing object to the dimensions needed to simulate a certain section of the real world. In the figure, vehicles are used to explain the concept of abstraction. Software for a vehicle enthusiast and software for a scrap merchant contain different abstractions or classes for objects. Therefore, depending on the type of abstraction, a class can contain different aspects of an object.
An understanding of the relationship between classes and objects is a prerequisite for completing the following lessons successfully. UML is a globally standardized modeling language. You use it for the specification, construction, visualization, and documentation of software system models. The different diagram types in UML represent different views of a system.
A class is represented by a rectangle in UML notation. A class can be represented as follows: name of the class, attributes of the class which is optional, methods of the class which is also optional. Attributes describe the data that can be stored in the objects of a class. They also determine the status of an object. Methods describe the functions an object can perform. They determine how an object behaves.
A class diagram describes all static relationships between the classes. The basic forms of static relationships are as follows. Association. A customer books a car at a rental car company. Generalization and specialization. A car, a bus, and a truck are all vehicles. Note, classes can also be shown in class diagrams with their attributes and methods. In this example of a class diagram, these attributes and methods have been omitted to improve clarity.
An association describes a semantic relationship between classes. The specific relationship between objects in these classes is known as an object link. Therefore, object links indicate associations. However, an association can also be recursive. In that case, the class would have a relationship with itself. In most cases, Recursive associations are used to link two different objects in the same class. Each association has two roles, one for each direction of the association. Each role can be described by an association name. Each role has a cardinality that shows how many instances can participate in this relationship. The multiplicity is the number of participating objects in one class that have a relationship to an object in the other class. Like all other elements of the model, cardinalities are dependent on the concrete situation being modeled. In this example, you could also require a cardinality of at least 1 to indicate that only someone who actually makes a booking becomes a customer of the rental car company. On the other hand, the cardinality of any number would allow for a more general definition of a customer. You can use role names at the end of the association lines to describe the relationships between the classes involved. In the example, a person could appear in the role of an employee or in the role of a company director. In the recursive association shown in the example, the roles of a child and parent are defined using role names. Two instances of the LCL person class have a relationship with each other and represent two roles. If association is used to link two classes, then a special class can represent this relationship. The characteristics of the relationship are described using the attributes of the association class. A dotted line connects this class to the association line.
Aggregation and composition are specializations of association. Aggregation and composition show that an object can contain other objects. The relationship can be described using the phrases consists of or is a part of. For example, a car consists of wheels and an engine among other things. Aggregation and composition appear as a line between two classes. They are labeled using a small rhombus. The rhombus indicates the aggregation or composition. Otherwise, the notation conventions are the same used for associations. Composition is a specialization of aggregation. Composition means the contained object cannot exist without the aggregation. For example, a car reservation cannot exist without the car rental agency. Therefore, the cardinality of this kind of aggregate is at least 1. The lifetime of the individual parts is linked to the lifetime of the aggregate. This means parts are created either at the same time as the aggregate or after the aggregate and are destroyed either at the same time as the aggregate or before the aggregate. In UML notation, a filled-in rhombus denotes composition.
Generalization and specialization relationships are always bidirectional. For example, the class LCL truck can be generalized as a special class of LCL vehicle. Generalization and specialization relationships are denoted by a triangular arrow. This arrow always points from the specialized class to the generalized class. The level of generalization increases in the direction of the arrow. Trees can be built up using these relationships.
An object diagram is a snapshot taken during program execution. It describes instances of classes and the relationships between them. It is not a new type of diagram, but rather a variant of the class diagram. It is only useful for representing a complex class diagram. Sequence diagrams are used to show certain processes or situations. A sequence diagram describes the sequence in which objects are processed and the interaction they have with each other. Sequence diagrams may show the following processes: when objects are created or deleted, when objects exchange messages. In UML notation, the object lifeline is represented by dotted vertical lines with a box containing the object name at the top. An X is used to indicate the end of the lifeline. The control focus appears as a vertical rectangle on the object lifeline. The control focus shows the active period of the object. Possible statuses of an object are as follows. An object is active when actions are executed. An object is indirectly active if it is waiting for a subordinate procedure to end. Messages appear as horizontal arrows between the object lines. The message is written above the arrow in the message parameter form. There are various ways to represent the reply. In this example, it appears as a dotted returning arrow. You can also include a description of the process and add comments to the object lifeline.
In delegation, two objects are involved in handling a request. The recipient of the request assigns the execution of the request to a delegate. In this example, the driver, that is the object driver, sends the message "Get fuel level" to the vehicle or the object car. When the message is received, the car sends a message to the tank, that is the object tank, to find out what the tank contains. In other words, the car delegates the task to the tank. If necessary, the car formats the information containing the current value of the contents of the tank before passing it back to the driver.